In chapter 4, we begin our exploration into what we call integrals, which, as I told you in the last video, is really one of the central ideas of Calculus 2. So especially for those of you who are going onto Calculus 2, you need to really pay attention because this will be most of the, a large chunk of the semester will be taking this idea and then having it blow up into all sorts of really interesting problems. But okay, to begin, as we talk about integrals though, we need to think about areas and distances and the relationship between them. So we're going to start with this problem where we have the function 10 minus x squared that I kind of drew an approximation over here. And our goal is to estimate the area between 0 and 3. So you can kind of see, if you just look on here, you can kind of see that it's that area right here. So the question is, how do we estimate this? We don't have any nice formulas that we can use to get this area exactly. Well, I mean, we will have them, but we don't right now. It's not like this is something you learned in geometry class. So the question is, how do we estimate? And the answer is you try to break your object up into simpler shapes that are easy to calculate. And it turns out probably the easiest shape is that of a rectangle. So let's draw a rectangle right here. That is not a very great rectangle. Let's come, that looks better, and then that looks better, and then that looks better. So you'll see we have 3 rectangles, and now we just have to ask ourselves, what is the height of each rectangle and what is the width of each rectangle, because we kind of know how to do this. So our area is approximately, I'm going to use a little wavy lines to say approximately, the area of the first rectangle. So I'm going to put area of R1 plus area of R2 plus the area of R3. And so now all I have to do is I just have to go compute what is the base times the height. And so now I'll use equal signs from here to say the area of that is this base times this height. The base is 1 because this went from 0 to 1, right? If I were to put notation on here, I've got 0, 1, 2, 3. So that base is 1, and the height is, it looks like the height is 9. So 1 times 9 plus, now this one, we have base times height. This base is 1, and this height is 6. 1 times 6. And then this base is 1, and this height is 3. And I know I didn't do a great job. My bases are not, my rectangles are a little wobbly. But I hope you all can deal with that. I know you're tough. And this is 1 times, and this height is just 1 itself. So how could I figure out those heights if I couldn't just tell by plugging them in, if I couldn't just tell by looking at the graph? Well, the answer is, this equation is y equals 10 minus x squared. And so I could put 1 in this equation. And so this could have been, I could put f of 1 in this equation and get 9. And that's that number 9 right there. And then I could put 2 in that equation and get that dot, which is 6. So if I do 10 minus 2 squared, I get 6. And then finally, if I do 10 minus 3 squared, I get 1. And so here's my 9, 6, and 1. They were found by just plugging this number, and this number into my equation to come up with the heights. So we'll have some formulas that we use at some point, but I'm going to encourage you to not focus on the formulas, but to just kind of focus on how it goes. I realize I'm probably just circled a number that wasn't even on the screen, so sorry about that. Okay, so that's our area. And our area turns out to be 9 plus 6 plus 1, so 16 is what we get. Now, if you're looking at this, you probably recognize that this is an underestimate because we have a bunch of area, leftover area. So we could make an overestimate if we wanted. And the way we would do that is instead of drawing our rectangles in this way, I might draw my rectangle like this. And that would give me a second rectangle. And then that would give me a second rectangle. And so notice if I use my red rectangles, I would also get an estimate of the area, but the red rectangles will be a little bit bigger than the area. So this blue was an underestimate versus this red, which is going to give us an overestimate. Okay, well, let's just calculate that area now and see what we get. And that area is going to be 1 times This time it'll be 10. Why? Because now I'm putting 0 in my equation. So 0 is the spot here. And now this rectangle is based on that height, which is based on the height x equals 1. And so I'll put 1 in my equation. And that will give me 9. So 1 times 9. And then finally, I'll put 2 in my equation because that's my height of my rectangle. My rectangle is what I get when I put 2 in my equation. And so I get 1 times 6. And now I put those together, and it looks like I get 25 for my estimate. So I don't know what the area is exactly, but I've got two estimates. I know it's bigger than 16 and less than 25. We're going to have names for these. We are going to call these right-hand, a right-hand estimate. So this blue we'll call a right-handed estimate, or right endpoints. You'll hear us call that at some points. Right-handed. How about if I say, what if we say right endpoints? That sounds even better. So these are using right endpoints. Why would I call them right endpoints? Because to calculate the height of a rectangle, I use the right-hand side of my rectangle. So if I look at this rectangle here, I used the right-hand side to determine the height. Versus over here with red, these would be called left endpoints. And maybe based on that conversation, it's easy to see because if I looked at this rectangle here, I would be using the left-hand side to make my estimates. Okay, so whenever you're given a problem, you're going to be given a bunch of problems, and you will be told two pieces of information. You'll be told how many rectangles to use and whether to use right or left endpoints. And so as you go through the homework, you'll be told those two things, and then you'll choose the correct type of endpoints, and you'll put the correct number of rectangles, and you'll make your estimates. So a large part of your homework, this section, is just going to be creating these types of estimates. But a big question that we want to ask, and this is the important one, is how do I get a better estimate? How do I get a better estimate on this problem? Well, there's a pretty simple way to get a better estimate. And the simple way to get a better estimate is to make your rectangles smaller. So use more rectangles. So what you could see is that if I took this problem, and I'm going to attempt to, oh, I think I just wiped it all out. Okay, now I'm going to try to draw it again, and this one's not going to look near as good, I think. All right, well, there's my effort, and we'll just deal with it. Okay, but now what if instead of using 3 rectangles, what if I use, say, 6 rectangles? So what if we did n equal to 6, and then what if we did, say, right-hand estimates, right endpoints? What would we get? Well, now notice our picture would look like this, and I would have that rectangle right here, that rectangle right here, that rectangle, that rectangle, that rectangle, and that rectangle. And so now notice how less white space there is on the side, and that's because our estimates has become better and better. And so we could calculate this. How would I calculate this estimate? The way I would calculate this is I would take, well, my first point, and how would I come up with this height? So I would do my area would be the base times height plus base times height plus base times height. So I would do that each time. But let's look at my bases. My base, in this case, is now going to be 1/2. So I'm going to have 1/2 times, and this height right here is what I get when I put 1/2 into my equation. So let's put 1/2, and then I'm going to write an f of 1/2 here to represent that I'm putting 1/2 into my equation. My second rectangle, its base is also 1/2, but now its height is given right here, which is given by putting 1 in my equation. So I'm going to put 1/2 in my equation, then I'll put 1 in my equation. And I'll keep going through this way. And let me erase this picture because you've got it in your head. You probably got it drawn on your somewhere in your notes. If you're taking notes, I hope you are. I think it would probably help you. and then we'll go plus 1/2 f of 1.5 plus 1/2 f of 2 plus 1/2 f of 2.5 plus 1/2 f of 3. There we go. And so we would have to plug all of these in, and hopefully we would get ourselves an answer. And so when we do all this, we get 1/2, and then f of 1.5 is what we get when we, or f of 0.5 is what we get when we put 0.5 in our equations. That's 10 minus 0.5 squared. And so this is 9.75. And then f of 1 is what when we do 10 minus 1 squared, and we get 9. And then f of 1.5, we do 10 minus 1.5 squared, and we get 7.75. And I'm going to stop there. Okay, and we just keep going all the way along. And then if we do this correct, we get ourselves a really pretty good answer. Give me just a second, and I'll calculate that out for you. So plus I'm working on it. Oh, I messed up. Okay. Let me try it again. Okay, let's do that. Okay, so if I did it all right, I got 18.625 when I calculated that out. Sorry for the delay, but you know, it's just like we're in class. We would sit there and stare at each other while someone calculated this out as well. So 18.625, what you'll notice is that this is an even better estimate than the past one. So the last time we had 16 and 25. This is in the middle, and so this is an even better estimate. If I wanted, I could go make left-hand endpoints and get an estimate that's a little bit bigger, and then we could kind of start to sandwich this. And then instead of using 6, we could do 12 or 24 or 10,000, right? So notice that by the time we had 10,000 rectangles and we used this process, our picture would look really, really good. So if we had some sort of graph function where our function looks like this, and we're trying to find, say, that area, and I did 10,000 rectangles, then each rectangle would be just super, super tiny. And what you would notice is that there'd be very little extra space left over at all. And the more and more rectangles you have, the closer and closer you get to our answer. Okay, so this brings us to this brings us to, and by the way, I'm flipping over the page in my notes. This brings us to the idea of kind of coming up with a generalized formula or generalized way of doing this. I'm not going to ask you to kind of use this formula in its form, but I do hope that it makes sense and you can understand. So what does a formula look like? Well, what a formula looks like is we add up all of the rectangles, R1 plus R2 plus ... plus Rn. So we add all of our rectangles up. And let's look at each rectangle individual. So let's look at this one and say, what is the width here? Well, the base of one of the rectangles, we're going to call, the base of every single rectangle is going to have the same width because every rectangle is the same, and we're just going to call our base delta x. That seems like a pretty reasonable answer, doesn't it? And then our height is right here, and our height is going to be what we get when we put whatever x value this is into our function. And so this will be like x1, x2, x3, x4. And so this first one, we're going to take our first value and put it in our equation and then multiply that by delta x. So this is our base times the height. Then we're going to take our second value, put it into our equation, and multiply that by delta x. And then we'll keep going all the way across until we've done this for every single value. And we'll have, let me erase my picture so that we can see. And then we'll have f of x in plus delta x. So what is this formula saying? This formula is just saying do base times height, base times height, base times height. Oh, that's a multiply. Base times height, base times height, base times height, all the way across. And by the way, sometimes you'll see this written in a little prettier form, and that is f of x1 plus f of x2 plus f of xn times delta x. So sometimes people will just factor out all the delta x's to put it in the end. If you want to, you can do that. So you can just add up all the x values and multiply by delta x when you're done. These x's, these x points, x, are called sample points. And those sample points can be chosen anywhere within the interval. So if my picture looks like this, and I have my graph here, and I've drawn my rectangle, so suppose I'm finding this area, and I have my little rectangle that I've drawn here, I can use any point in here as the sample point. So I can use the right-hand side, I can use the left-hand side, I can use somewhere in the middle. I can use any point in that rectangle as my sample point. Okay? Now, what is the area exactly? Well, the exact area, this is just an approximate. How would we go from approximate to exact? Well, we let those number of rectangles get larger and larger and larger. And what does it mean to let it get larger and larger and larger? It means we take a limit. And we take the limit as the number of rectangles approaches infinity of that equation. And you know, it's possible that we can, in the simplest possible problems, we can actually take this equation and solve it and come up with a solution for find the limit exactly. In general, though, we're not using this equation as something we compute with. This is not something that we do math with, but it's something we always think about because this tells us how to think about the area and what we're calculating. But we end up using different techniques usually to find the area. Okay, let's do another exercise. Let's do exercise 4.2. And in exercise 4.2, we're going to tackle the exact same problem, but this time we're going to change where our sample points are. So we're going to do sine of x. We're going to do sine of x from 0 to pi, and we kind of know what sine of x looks like from 0 to pi. It goes up, and then it comes back down, and so here's pi. So here's our sine of x function. And so we're trying to find this area right here. But it gives us an interesting note. It says use the sample points as midpoints. So instead of using the right or the left of each rectangle, we're going to use the middle of the rectangle. And that actually makes our answer even more precise. In Calculus 2, you'll find some other ways to make it more precise. We'll instead of drawing rectangles, you'll draw trapezoids, and then you'll draw like little boxes with parabolas on the top, and that'll be called Simpson's rule. So you will get more sophisticated ways to do this in Calculus 2. In Calculus 1, we're only going to be drawing rectangles. But if you use midpoints, that kind of usually gives you the best estimate we can do here in Calculus 1. Okay, so we're going to go from 0 to pi, and we're going to use 3 intervals. So that means my first interval's here, my second interval's here. So if I'm going to take this, I'm going to divide it into 3. And so that means this is pi over 3, and this is pi over 3. But now what I need to do is I need to draw my rectangles using the middle. So that means I'm going to use this middle point for my rectangle. And what is that middle point? Well, halfway between 0 and pi over 3 is pi over 6. You could do this by just adding 0 plus pi over 3 and dividing by 2. Or you can kind of just think about fractions. Okay, and then finally, between pi over 3, this is 2 pi over 3. So halfway between pi over 3 and 2 pi over 3 is pi over 2. And again, you could add those two together and divide by 2, or just think about fractions. And there's that one. And then finally, here's this one. The nice thing about midpoint, and the reason why it gives you a little better estimate, is notice we have a little bit of area. In a little place, it's an overestimate, but also in some places, it's an underestimate. And so those tend to balance each other out, giving you a decent estimate. But now notice this white area and this colored area are not the exact same, so you're not going to get perfect answers. But your answers tend to be better than if you just chose one extreme or the other. Okay, so we'll do sine of x using midpoints, using these three and see what we get. And by the way, this is a great time for you to pause. If you've not already paused, now's a great time for you to pause and see if you can calculate this out yourself. But I'm going to go ahead and write it down. So our area will be approximately, well, we'll do f of pi over 6 times, and what is each width? Each width is pi over 3 here. And then we'll go plus, I'll tell you what, let's lower this down a little bit so I can actually write it all the way out. F of pi over 6 plus, or times, pi over 3. This is our f of x1. I'm just going to use that formula we had a second ago, delta x. So our first point is pi over 3, and delta x is this width right here. And then our next one is going to be f of pi over 2 times pi over 3. By the way, your delta x should be the same each time. You know, in a theoretical class, like you might take in a graduate school, you can switch them around. But in calculus, we never switch them around because it's the easiest thing to do is to make them always be the same. And then finally, we have this last one, which needs to be 5 pi over 6. And so I'll do f of 5 pi over 6 times pi over 3. And so now I just need to put these in my sine functions. So this is actually sine of pi over 6. This is actually sine of pi over 2. And this is sine of 5 pi over 6. Let's see, these are ones that we know. I'm trying to remember, what is sine of pi over 6? Is that going to be 1/2 or square root of 2, or square root of 3 over 2? You all have a really clever way of thinking about it. I think that one's 1/2. Yeah, it is. Let me just check, just for just to be clear. Sine of, these are things that I often get right in class because I'm not worried about. Sometimes on the video, it's like for some reason it's harder on the video. Okay, so this is 1/2 times pi over 3 plus, and sine of pi over 2 is 1. So this is 1 times pi over 3, and 5 pi over 6 is also 1/2 times pi over 3. And so you put all those together, and it looks like our answer when we add all these together is 1, so we end up with 2 pi over 3 for our answer. So 2 pi over 3 is what you get. If you wanted, we could make that into an exact answer, and it would be 2.09 would be what it is as a decimal. But I think 2 pi over 3 is a better approximation than 2.09. Okay, so that's how we do these problems. And so this is going to be a big part of your homework. So in your homework, you're going to have to do a couple of these where you're given a function. Either you're given a graph and you're just to estimate by looking at the graph, or you're given an equation, you have to plug numbers in your equation and create these estimates. So I want you to be really good at creating these estimates, because we're going to talk about how to use fancy calculus to find these answers, but it turns out these estimates always work, and there are a lot of problems that you can't do with fancy calculus, and so you have to use estimates. And if you ever happen to use calculus outside of a math class, which I know is actually a little bit of a stretch maybe, you're probably more likely to do an estimate like this than you are to do it exactly. Okay, but let's come over, and what I really want to do now is make a connection between this problem and what I call the distance problem. So we're going to have a similar type of problem that we call where we calculate distances. And so what I'm going to do is I have that table on there. So velocity of a car is given by this table, where at time 0 it's going 22 miles per hour, feet per second, and then at 2 seconds it's going 18 feet per second, 4 it's given 14, 6 it's given 10, and 8 it's going 6 feet per second. So we know everywhere during these 8 seconds, so it's like you have the car is driving for 8 seconds, and we know that this is how fast it's going at each moment. And so we know it at 0, 2, 4, 6, and 8 how fast it's going. So what we're going to do is we're going to try to just find both an upper bound and a lower bound for how far that car has traveled. So let's start by going on an upper bound. And this is how we're going to think about it. So for our upper bound, the way we're going to think about it is between this time, between the 0 and 2 time, how fast is the car going? Well, between 0 and 2, the fastest the car ever goes is 22 miles per hour, or 22 feet per second. So the furthest it could have possibly gone between time 0 and time 22 is 22 times 2 seconds. Notice that's because that's the fastest it was going, and if it went that fast for 2 seconds. So suppose it went 22 feet per second the entire time, and then just right when it got to the 2 seconds, it dropped down to 18. We know it doesn't do that. The cars tend to smoothly speed up and slow down, but we know that every speed here is between 22 and 18. So if we just use 22 for every speed in that whole second, that's going to be the fastest it could have been going. Okay. Now let's do the same thing for the 2 to 4 section, and say what is the fastest that it could be going here, and the fastest it could be going here is 18. So that's the fastest it could be going on this section. So we'll do 22 plus 2, and then that second section, 18 times 2 is the furthest it could have gone. So 44 feet is the most it could have gone. So it went less than 44 feet in that first 2 seconds. And it went less than 36 feet in the next 2 seconds. Okay, let's just keep going here because we can kind of see how this is going to play out. And we'll do plus, I'm going to have to drop down to the next line. 14 times 2, and then 10 times 2. What about this last 6, you might say? Well, notice if I'm thinking about 8 seconds, there are really only 4 segments. There's the 0 to 2 segment, the 2 to 4 segment, the 4 to 6, and the 6 to 8 segment. There really isn't an 8 to 10 segment because we're stopping at 8 seconds. So I put all these, and these give me an upper bound of 44 plus 18 plus. Okay, let me do this real quick. And I got 128 feet for an overestimate of how far this car went. Well, okay, now let's see if we can make a lower bound, kind of using the same type of concept, except now I'm going to come and look at each segment and say, what is the slowest the car could have been going in each segment? So here, the slowest it was going was 18. So this first segment, a lower bound, so the car went at least 18 times 2 feet during that first second, because we know it's going faster than 18 during that whole segment of time. So it went at least 36 feet. So in some ways, you can look at this first segment and you can say, okay, its speed went from 22 to 18 feet per second, so its distance was between 88 and 36 feet during that section. So notice we used 44 and 36. Notice we used the 44 for the upper bound, and we used the 36 for the lower bound. Okay. Now we're going to do the same thing. So for this segment, the slowest it could have been was 14 for that second segment. So so here it's going. The speed is always between 18 and 14. So the slowest it could have gone would have been 14. So this is 14 times 2. And then finally, we'll keep this up, and we'll do 10 times 2 and plus 6 times 2. And so now we put all those together, and that gives us our lower bound, 18 plus 14 plus 10 plus 6. Each of those times 2, and we get 96 feet. So what do I know about this car? I know this car went somewhere between, it went at least 96 feet because that used the smallest speed in each interval, and it went at most 128 feet because that used the largest speed in each interval. And we added the 4 intervals together, and that gives us our estimate. What I hope you're seeing is that these calculations look a lot like what we did just a moment ago, what we did earlier. They look like we have we put a value in, so it looks like we took the velocity at some sort of time 3, and then we multiplied that by a change in time. So notice this 2 is because each segment changed by 2 units. So it's like we have a velocity times a change in time. So this looks a lot like what we did in the last problem. And notice, if I were to think of this car as a graph, if we were to think of this car as a velocity graph, and I were to draw a picture where my velocity starts at 22, then goes to 18, then 14, then 10, then 6, and put some sort of curve on it, this 22 times 2 is just that rectangle right here because it's base times height. And that's how long it went times how fast it was going at the beginning of the interval. And if I took that second one, it would be like that rectangle, and that rectangle. So what I really did was when I did this problem, was I really took two estimates, using, on the first case, left-hand sample points, and on the second case using right-hand sample points. So what I want you to see is that this problem is the exact same problem as the problem I did earlier. We've just worded it and disguised it in this language of distances and velocities instead of talking about areas and the heights of the function. So again, how would you go about making estimates better for the distance problem? You would use smaller rectangles. You would get more samples. So instead of measuring the speed every 2 seconds, you'd measure the speed every second, and that would give you a better estimate. If we wanted to measure the speed every half second or every 1/10 of a second, that would give us better and better and better estimates. So if you turn over to page 90, you'll see that there's a task that says, could we make even better estimates if instead of knowing the table, we knew the function that the table came from, and that is v, that's a horrible v, and that is v of t equals 22 minus 2t. By the way, that actually, I think, is the equation that works. So if you do 22 minus 2t, then you have this equation right here. If I had this, could I use 8 intervals to estimate my total? And the answer is yes. What would I do? My total distance, I would just do v at 0. Let's see. Oh, and we could use midpoints of each interval. So I would just do v of t1 times my delta t plus v of t2 times my delta t plus. And then what we would do, I would solve that problem the exact same way I solved the problem on exercise 4.2. So this is the same as 4.2, except we're using this equation, using that equation instead. Okay, and so let me just give you a little bit of a sketch. Since this problem goes from 0 to 8, each of our intervals, we went from 0 to 8, and if we divided up into 8 segments, 1, 2, 3, 4, 5, 6, 7, 8. So if we had 8 segments, then notice we would just be using our units here. So each width would be 1, so the delta t's would be 1. So our distance would be something times 1 plus something else times 1 plus, and then we would go all the way across. And then since we're using midpoints, we would take the 1/2s. So I would put 1/2 here, 1.5 here, and then etc. So I would put 22 minus 2 times 0.5 times 1 plus 22 minus 2 times 1.5 times 1 plus, and then dot, 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 and we would keep going all the way until we get to 7.5, and that would be our last estimate. And then we would have our estimate for this problem. And there you go, and that's what we would get for our answer. And I'm not going to calculate that out exactly. I'll let you do that on your own. But I want to make it just some final conclusions as we end this video. I feel like there's a lot going on, but hopefully you can do some of these problems. The final conclusion is, what do we notice? We noticed that we had 2 problems. We had the area problem that we started with, and the distance problem that we ended with. Okay. Well, what did this exercise, what did I really want you to take from today? Well, one of the big observations I wanted you to make was that these are actually the same problem. And what you'll find is that when you get into Calculus 2, you'll figure out lots of problems that are equivalent to these two. And the way the problems are done is anytime you're taking one segment and breaking up into small pieces and multiplying a value on that piece times a small segment, then you're actually doing a problem that's the same as the area problem or the same as the distance problem. But what's important is that this actually gives us some clue as to how we should go about finding the area. So if I know velocity and I want to get to distance, what do I need to do to get there? Well, the answer is I need to do an antiderivative. Right? If I know velocity and I want to get to distance, I know I need to take the antiderivative to make that passage. Well, since the area problem is the same, if I have a function and I want to find the area underneath, the area underneath the function, what do you think I'm going to need to use? I'm going to need to use an antiderivative. And this is one of the big ideas of the semester, and that is that finding areas is somehow the opposite of finding derivatives. So let me just come back and say one of the big things that we said kind of at the beginning of the semester, and that is that the semester is built on two problems. One problem is you have a graph and you want to find the tangent line to the graph. And the second problem is you have a graph and you want to find the area underneath the graph. Well, these two problems feel entirely, like entirely separate problems. They don't feel like there's a lot related to them. But what we're starting to see, and this is going to be one of the big ideas that we come up with in the next two sections, what we're starting to see is that this problem, to do this problem, we use a derivative, and to do this problem, we're going to need to use an antiderivative. So these two problems that feel like they're 180 degrees apart from each other, they feel like they are just completely going in different directions, they're actually the same problem. One, we do the derivative going one direction, and the other we do the antiderivative. So these problems are somehow like opposites of each other. And that's one of the big ideas this semester. So when we come back next time, we will start using a little bit of notation. We'll introduce the word, what we call an integral, and we'll start using a little bit of fancy notation to describe this stuff. But the ideas stay the same as the last two chapters. So if you understand how to calculate antiderivatives, and you understand how to do kind of this estimating method of doing these, breaking up into segments and calculating the areas, if you can do those estimates and you can do antiderivatives, then everything for the rest of the semester is going to be really simple. It's just using new notation and new words to talk about those same two ideas. So I'll see you in section 4.2. Oh, real quick. 4.1 homework, I felt like it was a little bit long. It almost felt like we had a little bit excess amount of busy work. So I decided to reduce it a little bit. If you want, you can do just these four problems. Just number 1, part A, number 5, number 13, and number 17. And I think if you do those three and you're like, I've got it, I can do, because these are all these problems are kind of somehow taking your graph and drawing rectangles on it. So if you can do those problems and you're really good at drawing your rectangles and come with your estimates, then I think you're good to go. If you look at those problems and you go, oh, I'm still struggling, I'm not getting them right, I'm not doing it correct, then here are 3 extra problems you can do that'll kind of give you more practice on those problems. But if you've got these 4 and you feel good, feel free to move on to the next homework assignment. Okay, I'll see you in section 4.2.